Everybody have a good weekend? You know, everybody finished their homework?
I was wondering if we could turn that in Wednesday instead of Monday, because I write down a bunch of notes on my homework, like formula-wise. I'd like to study it before I turn it in.
That's fine. I can turn it in on Wednesday. Same for everyone else. Now, let's see. Speaking of homeworks, Colton Mashburn, Hunter Turnage. There you go. All right. Last time we were talking about dielectrics when the clock so rudely interrupted us. What do we back up and make sure we know where we're at? And we're talking about a capacitance. We can talk about the two parallel plates. That their capacitance is determined by epsilon sub naught times the area of the plates divided by the gap between them, the distance by which they're separated. And epsilon sub naught is the permittivity of free space. Strictly speaking, that's what you would have if your capacitor was filled with vacuum. Now, if it's filled with air, and what was epsilon sub naught? It was 8.85, yeah, 8.85 times 10 to the minus 12. Make sure I get the units right. Coulomb squared per Newton meter squared. That is for a vacuum. Yes, times 10 to the minus 12. Air is not a vacuum, but in order to get the value of epsilon in air, you would multiply epsilon naught by the constant for air. Which for air, the constant K would be 1.0006. Is it 3 zeros or 4? 3. Now, first thing you notice. And when we multiply epsilon sub naught by the coefficient, the dielectric constant of air, it doesn't change anything until you get out into the fourth decimal place. So, here in class, we're going to consider the epsilon sub naught of free space is the same value when you're talking about air. Because as far as closely as we can measure it, it is. multiplying by that constant isn't going to change any of our significant digits. But what if that dielectric was something else? What would epsilon be? What would the permittivity be for, say, paraffin? It would be the dielectric constant of paraffin times epsilon sub naught, the permittivity of free space. And on page 485 in table 17.3, you can see that the dielectric constant K for paraffin is 2.2. Suddenly, that's no longer, suddenly it matters. Now it's definitely going to change the value of epsilon when we start calculating the capacitance. Yes? You've got, I don't know what's going to be on the test, but they're here in the book, so you can certainly put them on your index card. What I want to make sure we understand right now is the effect of this dielectric constant. The dielectric constant for a material gives you the permittivity of that material, the epsilon of that material. So what would the effect be if we put a paraffin dielectric in that capacitor? We have a capacitance, and it's equal to epsilon sub naught times the area divided by the gap. And let's say that's equal to 5 times 10 to the minus 6 farads, or 5 microfarads. Now that's with an air gap. We don't know what the area is, we don't know what the gap is, but we know we've got a capacitor. We've got two parallel plates of some area and gap that in vacuum or in air would give us 5 microfarads of capacitance. What would happen if we then injected paraffin into that gap? How would it change the capacitance? It would change epsilon sub naught would become epsilon for paraffin, which is equal to K for paraffin times epsilon sub naught. So C would then become 2.2 times epsilon sub naught A over D would be equal to 2.2 times 5 microfarads. It would just make the capacitance 2.2 times bigger. Have any of you read the book to look at the mechanism of why this happens? Because it's kind of convoluted. We've got two parallel plates. We've set up an E field between them. there is a voltage. And, wait, what am I looking for here? Yeah. This voltage is equal to the E field times the distance between them. Okay? What happens when we put a dielectric in here? I'm going to change colors here. What happens is, depending on the permittivity of that dielectric, it's going to develop charges. But not everywhere. And where it does develop the charge, the E fields then get disrupted. That means the E field inside that dielectric is reduced. Okay? There is the E in here in the dielectric is less than the original. Okay, that's not going to work. The initial E field. What's the voltage across the plates? The voltage across the plates is equal to the E field times the gap between them. Well, the gap doesn't change, but the E field does. So we now have a smaller V. The voltage is less because the dielectric E field is less. And if the voltage is less, what has happened to the amount of charge that's built up on these plates? The Q. The Q is the same. It still has the same amount of charge built up on both sides of these plates. So Q is constant. Q is the same. But Q is equal to what? Capacitance times voltage. So if voltage went down, then capacitance had to get proportionately larger in order for the Q to stay constant. Think this through. You've got two parallel plates. You've got a voltage across them. That means they've built up a certain amount of charge. Now you come in, you sneak in there, and you slide in this dielectric. The amount of charge doesn't change. What would happen that you would be able to measure? The voltage would go down. The voltage for that amount of charge would go down. Now, if you had it affixed to a voltage source that produced that forced it to keep it at the same amount of voltage, what would happen is the amount of charge would then, that supply would then provide more charge to the plates to drive up the amount of Q to maintain the same voltage. Because as you insert the dielectric, capacitance is going to go up. And if the voltage stays the same, then the amount of charge has to go up. Okay, does everyone understand what's going on with these dielectrics? We understand how to calculate a new epsilon for a new dielectric. And do you also understand that if you're given the amount of the capacitance and then you're told now you stick in this dielectric, how does the capacitance change? All you have to do is multiply by the coefficient. You don't need to go back and recalculate the whole problem. All right, let's look at the amount of energy that is stored in a capacitor. We're in 17.9, which is on page 486. Now, you understand that when you apply voltage to a capacitor, the net effect is that you're moving charge off of one plate and you're putting it onto another. Now, since this is a conservative force, the electric field, E field, the work done by the field, it's conservative. What does that mean? It means that it doesn't matter whether you take this charge, this negative electron here, and move it directly across to here, or if you take it and you move it way out here and down through some long fortuitously circuit, until it comes all the way back to here. What matters is that the electron moved from here to here across this potential difference. The distance it moves doesn't matter. The displacement is what matters. This is going back to physics 1, the difference between distance and displacement, conservative forces. Okay, the point is, this electric field has to do the same amount of work, no matter what path the electron takes to get from here to here. So, what is the work done by the field? Let's we're probably due to leave that up there. Now, the work done by the field is the charge and the voltage divided by 2. Now that voltage is actually the difference in voltage. Okay, I want to make sure everybody understands. Anytime we talk about voltage or potential, we're talking about the difference in potential. Because if you're familiar with circuits, you know that you can arbitrarily pick any point in the circuit and define that as 0 volts. And normally you would do that, you would define ground as your 0 volt. Okay? Sometimes if you're working with point charges in fictional hypothetical fields, you'll define 0 as the potential at infinity in order to mathematically handle talking about the absolute value of a potential at a point in space. But always your potential has to be a difference. It has to be a relative to some arbitrarily chosen 0 point. So here we're talking about the difference in voltage, in this case, across the plate, across the capacitor. And that's the total work that's done. We also know that the potential energy, anybody remember what that is? Same thing as the work. Although we generally define the work as the negative of the work was the change in potential energy. But we're still talking about the change in energy, the work done.
I thought it was the constant, then Q1 times QC over R.
Show me what you're looking at.
Electric potential energy, E equals K times Q1 times QQ over R.
That's E, that's KQ over R is voltage. So the voltage times the charge is equal to the, what you have there written anyway.
Okay.
Yeah. Now, we also, don't forget, we know Q is related to the voltage and the capacitance by this equation. Q is equal to the capacitance times the voltage. So what happens if we replace that here? We end up with capacitance times voltage over 2 is our potential energy, is our work. I would point out that we could also solve this for V and write V is equal to C divided by Q. Or I'm sorry, we could do that, or we could write V is equal to, yeah, no, I did do that backwards, didn't I? V is not equal to Q over C, C over Q, it's equal to Q over C. Yeah. So if we substitute this in for V, we end up with everybody see how we get these formulas, these equations? Yeah, okay. Let's look at this because they have a point. It is, this is oftentimes what matters is how you think about these things. And they point out that it is often useful to think of the energy stored inside a capacitor as being stored in the electric field. That doesn't make sense, right? Because when you move charges, it's the E field that does the work. Or when charges are moved by the potential, it's actually the E field that's doing the work. So let's look at how this relates to the E field. What do we got? Which one are we going to work with? CV squared? Okay, we've got, first we can replace C with what? Times V squared over 2. But what is V? Could be, but in this case, we want to get it in terms of the E field. It's just the E field times the distance between the plates, or the E field over the distance, change in distance. So, yeah. So this just becomes where one of these D's cancels out here. In the book, they rearrange it. I'll rearrange it the way they did. So you'll recognize it when you see it. Now, do you recognize that this product, the area times the distance, is simply the volume of the space of the E field? What this does is this sets us up with a useful concept called energy density. If we take the potential energy and we divide it by unit volume, we end up with this divided by the volume, and that gives us an energy density. Energy density is an important concept for you to understand. That's why these lithium-ion batteries they've actually gotten hazardous. They've improved the efficiency of batteries with lithium ions to the point that those things can pack some serious energy density. And you internally short one of them, you got a lot of energy being dissipated in a very short amount of time. What does that cause? Lots of heat, lots of expansion. Doing it very fast, you have an explosion and a fire. Energy density is important for all of you, so wrap your minds around that. There is some research going on down at UT, University of Texas, down in Austin, where they've actually done some research down there. They've come up with a new way of doing lithium-ion batteries, where instead of a liquid or a gap or liquid or whatever gap between them, they actually fill the gap, the dielectric in the gap, with a type of glass. It's solid. Now, and yeah, it doesn't make a lot of sense taking, and in fact, that one of the consequences of their results is that people had to start rethinking how they think about the effects of dielectrics going in, in terms of the energy of the charges being transferred. They had to rethink their thinking on the mechanism of how the charges were redistributed between the plates and things. But remember, we're talking about conservative forces. Doesn't matter how far those charges have to travel to redistribute. All that matters is their change in position, the beginning to end. Well, think about the consequences of a basically a solid state battery, a lithium-ion battery with, how many of you understand why why does it take so long to recharge a lithium-ion battery? Because if you recharge it too fast, you start producing what's called dendritic growth, little dendrites, little cat whiskers, hairs that'll start building up and growing off of those plates. They're actually metal deposits, like electroplating, but they grow in little whisker shapes. What happens when one of them grows all the way across and touches the other plate? You have a short, and with that short, you have a sudden and dramatic release of a lot of energy because they have extreme energy density. By putting a solid dielectric between them, you can pump electrons into that puppy as fast as you can. The dendrites cannot grow through solid material. They ever get that new technology to market, you're going to see that'll be a sea change, one of those seminal moments in technological development. But I digress. We were talking about energy density. Pretty much covered it. Any questions? We got about 20 more minutes. Well, I'm looking at that. Here it is. Yeah, we got about 20 minutes or so, give or take, 15, 20, something like that. Do any of you have any questions on any of the material we've covered up to date? Homework assignments, questions? Anything that may be coming up on Wednesday's exam that you want to ask questions about, other than what's going to be on Wednesday's exam?
I had a question on the homework, number
55? A homemade capacitor is assembled by placing two 9-inch pie pans 4 centimeters apart and connecting them to the opposite terminals of a 9-volt battery. Want to know the capacitance, the charge on each plate, and the electric field halfway between the plates and the work done by the battery to charge them. And then which of those values would change if a dielectric were inserted? Okay. Which part do you want to ask questions about? Okay, how would you calculate the capacitance of 2 parallel plates with an air gap between them? And I would ask you to pay particular attention to what I did not just erase. Why? Okay, what is... No, area doesn't change anywhere in this. When you calculate the capacitance, you need the area of the plates. What does it tell us about the plates? 9-inch diameter. Radius is 4.5 inches. What's the area of that circle? Somebody with a calculator, help me out. Say again. What? Square inches. Okay. How far, what is the gap between them? Say again. Yeah, 0.04. Okay. So what is our problem at this point? We've got an area in square inches and a gap in meters. So, first thing we would have to do is convert 4.5 inches. We could just convert that, but just to keep from getting confused when we start doing a conversion of square centimeters per square inch, let's just start by converting the 4.5 inch radius into centimeters. What's that? 4.5 times 2.54. 11.43 centimeters, or 0.1143 meters. Now, what is our area in square meters? Someone do the arithmetic. Say again. 410 square meters. Okay, 0.1143 squared. Okay, and then when you multiply by pi, say again? 0.04 square meters. All right. Does that sound reasonable? One square meter would be so big, so something this big, about 0.04 meters squared. All right. Now we know the area. We know the gap. What's epsilon sub naught? Times are they really both coming out to 0.04 meters and 0.04 square meters? They are. Like they would. So what would that give you for capacitance? What's your capacitance? Oh, I long for the days of chalk. Say again? Well, it's this many picofarads. Oh, I don't. Of course. Just think about your answer here for a minute. What are we given? Two significant digits. But here we're told 4 centimeters. One significant digit. What is this to one significant digit? Nine times 10 to the minus 12 farads, or 9 picofarads. All right. What else do they want to know? What is the charge on each plate? How do you calculate the charge? given the capacitance and the voltage. We know the capacitance is 9 picofarads. What's the voltage? 9 volts. So 9 times 10 to the minus 12 times 9. Say again?
8.1 times the negative 11.
8.1 times 10 to the minus 11. Well, yeah, that's right. Or 81 times 10 to the minus 12. 9 times 9 is 81 times 10 to the minus 12. So 8.1 times 10 to the minus 11. All right. What's the E field in the middle of this?
You still would equal voltage over distance, right? So that would be 9 volts over 4 centimeters.
Okay.
But you have to take the percentage back.
9 divided by 4 centimeters, or 4 times 10 to the minus 3. No, minus 2. Four centimeters. Right. How many significant digits do we have? To one significant digit. 200 what? Newton meters per coulomb, or volts per meter. Why do they ask you for the electric field halfway? What difference does that make? How is it different at the halfway point than it would be at a quarter of the way from either edge? In this case, it doesn't matter. The parallel plate capacitors, the E field is uniform and constant throughout the whole space. They were throwing you a curve. See if they could trick you into sticking in a factor of 1/2 somewhere that didn't belong. Okay, what's the work done by the battery to charge the two plates?
1/2 times 9.1 or 9.1 times 10 to the negative 12 times 9 volts squared. Which is 4 times 10 to the negative 12. Yeah, negative 12.
Say again?
The answer should be 4 times 10 to the negative 12.
4 times 10 to the negative 12? Punch that through your calculator again. You got the mantissa, right? What's your exponent? To one significant digit, you are correct. It is 4 times 10 to the minus 10. What? What are our units?
That used to the Q
The work, I used 1/2 C times V squared. Half of the capacitance times the square of the voltage. The units will be joules, by the way. Finally, what of these things will change if you go in, stick in a dielectric? We know that the capacitance is going to change. That means the charge is going to change. The work is also going to change. Any more questions? First of all, did we answer your question? Okay. Everybody understands how we work that problem? Okay. I'm not sure what Sim B is, but all right. Everybody ready to finish their homework and do an exam on Wednesday? What do you still need to know? All right. I guess we'll find out on Wednesday.